Now we're going to see an important part of this section, which leads to the definition of a dimension of a vector space. Now, Theorem 4.11, this is on page 226. It's a very important theorem, and that theorem allows us to define dimension of a vector space. The theorem says that if a vector space has one basis with n vectors, then any basis for V has to have the same number of vectors. So if your basis has 8 vectors, let's see the consequences of this theorem first. Let's say I have a basis for a vector space that has 8 vectors. Then any other basis need to have 8 vectors as well. So any other basis that I can find has to have 8 vectors. So that leads to the definition of dimension of a vector space. So we can define the dimension of a vector space as the number of vectors in the basis. So that's why this theorem is important, because if we didn't have this theorem, then if I say, okay, the dimension of a vector space is 5, well, that means there are 5 vectors in the basis. What if I have another basis that have 7 vectors? Then the dimension would not be well defined. Okay, so that's why this theorem is important, and it's very easy to prove actually. Let's say, for example, here's a proof. Okay, let's suppose this is a basis. Okay, suppose S equals to V1, V2, all the way to Vn is a basis for V. Okay. All right. What happens if I pick another basis? Let's say here is an S2. Okay, another basis. Let's put U1, U. Well, it should be U, not V. I don't want it to be the same. It could be different vectors, but let's say it's another basis. U2, U3, all the way to UM. Okay. Let's see what happens. What if M is greater than N? What happens if M is greater than N? Well, if I have more vectors, then there's a theorem that we studied before that says that if I have more vectors than the number of vectors in the basis, then those vectors are linearly dependent. Well, so this contradicts then. So if I say that this has more vectors than S, then S2 would be linearly dependent, but that's impossible because this is a basis. Okay, I forgot to say here, suppose S2 is another basis. For V. Okay, so if M is greater than N, S2 would be linearly dependent. That's impossible because we know that the basis vectors in the basis need to be linearly independent. Okay, what happens then if M is less than N? Well, then that would be a problem for S itself, right? If M would be less than N, then S would be linearly dependent. So that would contradict this fact here that S is the basis for V. So therefore, M needs to be equal to N. So they have to have the same number of vectors in the basis. So this would help us define the dimension of a vector space. dimension of a vector space is the number of vectors in a basis. See, it's okay to put the word a here, because you may say, okay, well, I can have many different bases. Yes, that's true. You can have many different bases, but it turns out that all of them need to have the same number of vectors. So this doesn't break the definition. So the definition is in fact well defined. Okay. So now we can see a few examples. So in R3, we saw there is the standard basis 1 0 0 0 1 0 and 0 0 1, right? This is a basis for R3, and it has 3 vectors. Therefore, dimension of R3 is 3. You may say, well, that's obvious because this is raised to 3. Well, dimension has nothing to do with this exponent. Dimension, it turns out that it's 3 because the basis has 3 vectors. The exponent 3 here is just part of the definition of the 3-dimensional space. Well, okay, let's see this example here. How about P3? We've seen that 1x squared x cubed was a basis. It was a basis for P3. So what is the dimension of P3? Dimension is 4. Okay. And you can also show that P2, the vector space of the polynomials of degree 2 or less, has dimension 3. So that shows how to compute the dimension, how do we find the dimension. It's totally based on this theorem 4.11. Now another thing is that if a vector space has only the 0 vector, then we say the dimension is 0. Okay, so if I say S is just a 0 vector, okay, so that 0 vector can only span 0 vectors, so the dimension is 0. So the span of S is actually just a 0 vector. Dimension of that span, oh, my notation here is horrible. My writing is horrible too. Dimension of span of S is 0. Okay. Then finally, you can take a look at theorem 4.12 on page 229. It says if you have a vector space of dimension n, then if you have any set with n vectors that are linearly independent, then that is a basis. So let me illustrate theorem 4.12 for you. So for example, let's say, I won't give you specific examples, but let's play with the numbers n for n. Okay, so let's say, suppose n is 5, okay? So dimension of a vector space is 5. Then if I pick, let's say, if I pick vectors, 5 vectors in that space, doesn't have to be. Maybe I don't know if it's. Maybe I don't know if it's a basis or not. It doesn't matter if it's a basis or not. If I know that, but if I know that they're linearly independent, then the conclusion is that it is a basis. So if I pick 5 vectors that are linearly independent, then it turns out that it's a basis. Another thing is that if I pick 5 vectors that spans the whole space, then that is a basis. So those two conditions, or those two consequences, come straight from the theorem 4.11. Okay. And that's the final theorem on section 4.5. Let me finish my writing here. Let's say suppose n is 5, and then if I have 5 linearly independent vectors, those 5 vectors form a basis for B. That's what number 1 is saying. And number 2, if I have 5 vectors that span that span V, then those vectors will form a basis.